For most of the structural materials, the modulus of elasticity for compression is the same as that of for tension. Sometimes in calculations, the tensile stress and the tensile strain are taken positive, whereas for compressive stress and the compressive strain are regarded as negative. So let's see what is a working stress. When designing machine parts, it is desirable to keep the stress lower than the maximum or ultimate stress at which failure of the material takes place. This stress is known as the working stress, design stress. It is also known as safe or allowable stress. We'll revisit maybe the working stress. We want to focus on the working stress. In designing machine parts, it is desirable to keep, or it is advisable to keep the stress lower than the maximum, or the ultimate stress at which failure of the material takes place. So this stress is known as a working stress or design stress. Sometimes it's known as a safe stress or allowable stress. It have got a lot of different names regarding the locality or where it's being applied. So also we would like to focus on the so-called factor of safety. This one is defined as the ratio of the maximum stress to the working stress. So mathematically, it is written as maximum stress over the permissible or the working stress or design stress. In case of ductile material, for example, mild steel, where the yield point is clearly defined, the factor of safety is based upon the yield point stress. In such cases, the factor of safety is equal to the yield point stress to the working stress or design stress or permissible stress. In case of brittle material, material which can easily break up once they are subjected to force, for example, cast iron, they tend to yield the yield point is not well defined as for ductile material. Therefore, the factor of safety for brittle material is based on ultimate stress. This is so special for this material which are brittle. Factor of safety is equal to ultimate stress to working stress. This relation may also be used for ductile materials. Note that the above relation for factor of safety for static loading. So the tensile test and for ductile and brittle materials. Let's see what is ductile material and brittle one. Tensile tests are used to determine the mechanical properties such as strength, ductility, elasticity, and stiffness. Ductility of a material is a property that allows it to undergo considerable plastic deformation under a load before failure, whereby the brittleness of a material is the property of a material of plasticity. This indicates how that material can behave, a property of plasticity before failure. A brittle material is one that breaks or shatters before it deforms, or It is the property of breaking of a material with a little permanent distortion. Brittle material, when subjected to tensile loads, snap off without giving any sensible elongation. Once they are subjected to a force, they cannot withstand the extension for so long, they break up. Cast iron is a brittle material. This is a good example for cast iron material. The tensile tester, how these are being tested in laboratory. A machine which applies a tensile force, a force that is applied in the opposite directions to the specimen, and then then measures the force and also the elongation. So we have to compare the elongation and the force applied to it. This machine usually uses a hydraulic cylinder to create the force. So the force applied is determined by system pressure, which can be accurately measured. Referring to the tensile tester, how is it designed or how is it working? So this is a machine for testing tensile stress. I've got an arrow that is indicating load, that is load indicator, clamps to hold here. Those are the clamps to hold here. Clamps to hold the specimen or the object that you want to measure. It is strength. So here, the material, down there is hydraulic in the cylinders, and load lever. So you'll be turning this until when the object will break up. In this test, a test specimen in the form of circular rod is prepared. Its ends are gripped in the tensile testing machine. It is then subjected to a gradual increasing tensile load until it fractures. During the test, the load and the extension reading are taken simultaneously. Stress is then calculated by dividing the load by cross-sectional area of the specimen. The load given, that is due to the pressure exerted by hydraulic in the cylinders, and the arrow indicating the size of the force. So you will get what? You get to know how much deformation in the material has been subjected to, that is stress. And for strain, the elongation, before it is fractures, before it breaks, there is a change from L1 to L2 over L1, original length, then the second length, you get the strain, that is the ratio, unitless. Step 1. Here you can see step 1, step 2, up to step 6. Step 1, original shape and size of the specimen with no load at all in that machine. Step 2, the specimen undergoing uniform elongation. Step number 3, point of maximum load and ultimate stress, tensile stress. You can see here the original length. You can see now the FF. It indicates that in step 2, steps undergoes uniform elongation, uniform. The entire body has been increased equally. Point of maximum load and ultimate tensile strength as well for step 3. Step 4, the onset of the necking plastic instability. Here you can see the necking is taking place in stage 4. Step 5, specimen fractures. It fractures here. It happens that there are 2 now. So you can return to original, to be in contact, so that you can measure now the total length that can be compared to original length. This being L1, this being L2. This is due to the force that we are pulling up and down. So that object was placed here. These are the 2 clamps here in between, we'll see later. So the force was pulling the other one up and the other one downwards. If these 2 are the clamps for the rod in between, so the force, and you have these levers to turn. Once you turn this, that means you cause the force within the cylinders is to push downwards, to pull downwards by turning these handles or this lever, rod lever. So in order to measure now the total length, you have to return this after fracture. You have to return until when they are in contact, then you measure the total length given. This is how the machine was working. Stage 1, this you can see there, stage 5. We had this necking stage here. The necking occurs as the sample leaves the elastic deformation region and begins to deform plastic. So necking, you can see at the middle, it breaks until when it breaks or it fractures here. So the classic cup cone shape of the fairly ductile tensile fracture is visible here. One can take now the vernier caliper to measure the length from the original length in comparison. This is a machine to indicate the force that was experienced during the testing, and this is indicated how the necking takes place. Compare the material properties of these 3 metal or 3 failed under tension. So this indicates how the structure of the atoms within the different materials, arrangement of atoms within the object. Stress-strain diagram. So we'll see, we have got a diagram to indicate how the stress and strain are proportional. In designing various parts of a machine, it is necessary to know how the material will function in service. That's the essence of knowing, of studying stress and strain. For this, certain characteristics or properties of material should be known. The mechanical properties mostly used in mechanical engineering practice are commonly determined from standard tensile test. So from the standard tensile test, we can come out with the certain constants, knowing that these different material behave in a certain property. This test consists of a gradual loading, a standard specimen of material, noting the corresponding values of load and elongation until the specimen fractures. The load is applied and measured by a testing machine. The stress is determined by dividing the load values by the original cross-section area of the specimen. So this diagram is very, very important to indicate how the stress and strain. This is our object or specimen, shape of the specimen after elongation. You can see the necking here until when there is a fracture here. There is a yielding point here, CD, and the A from O to A that indicates the proportionality of stress and strain. So this figure in totality indicates stress-strain diagram for a mild steel material. Mild steel material. The change in length are recorded by means of extensometer. So this machine will record the change in length. So here we want to see the proportional limit. We see from the diagram that from point O to A is a straight line, which represents that the stress is proportional to strain. Beyond point A, the curve slightly deviates. After point A, the curve tends to deviate from the straight line. This it is obvious that Hooke's law holds good up to point A. That means the Hooke's law obeys. This graph obeys Hooke's law from point A to from point O to A, and it is known as proportional limit. So part 2, that is elastic limit. When the load is increased beyond point A up to the point B, the material will regain its shape and size. From point A to B, the body being extended, or there is an increase in size, but in removal of the force, this body will return to its original shape or size. This property is termed as elastic. This means that the material has elastic property up to the point B. This point is known as elastic limit. It is defined as the stress developed in the material without any permanent set. So elastic limit is indicated or is shown where the object can return to its original shape after removal of the applied force. For our case, for our graph, it is from A to B. Since the above two limits are very, very close to each other, therefore, for all practical purposes, these are taken to be equal, to be 1. So point 3 is termed as the yield point. If the material is stressed beyond point B, the plastic stage will reach. That is, on the removal of the load, the material will not be able to recover its original size and shape, which is different from elastic, the point B. Now we are focusing from point B towards point C, where the material on removal of the applied force cannot return to its original shape and size, so it's termed as plasticity. So the strain increases as faster. the strain increases at a faster rate with any increase in the stress until the point C is reached. At this area, this portion, B to C, once the stress is increased, we found that the strain increases much, is no longer having the property of proportionality. That means that if the load applied is increased, that increase, the rate of increase is not proportional to the increase in strain because of plasticity. At this point, the material yields before the load and there is an approachable strain without any increase in the stress. Little stress, much strain can be experienced at this area or at this portion in our graph. In case of a mild steel, it will be seen that a small load drops to D immediately after yielding commences. Hence, there are two yield points, C and D. These points, C and D, are called the upper and the lower yield points, respectively. The stress corresponding to the yield point is known as a yield point stress. That is regarding to the mild steel material. At D, regarding to our specimen, at D, the specimen regains some strength and higher values of stresses are required for higher strength than those between A and D. This stress or load goes on increasing till the point E is reached. The gradual increase in the strain or length of the specimen is followed with the uniform reduction of cross-section area. As we have seen that the more you pull away that specimen, the area at the middle is being reduced. So this causes it now to have a smaller diameter, which becomes easier now for the tensile or for the stress. Does not require much stress because the area has been reduced. So that's why the gradual increase in the strain of the specimen is followed within the uniform reduction of the cross-section area. The work done during the stretching the specimen is transformed largely into the heat and the specimen becomes hot. This is a conversion of form of energy. Now it undergoes, it changes to heat. At E, the stress which attains its maximum value is known as ultimate stress. At E, the stress which attains its maximum value is known as ultimate stress. It is defined as the largest stress. Is termed as largest stress obtained by dividing the largest value of the load reached in a test to the original cross-section area of the test piece or specimen. So the breaking stress. After the specimen has reached the ultimate stress, a neck is formed. We have seen this. After the specimen has reached the ultimate stress, a neck is formed, which decreases the cross-section area of the specimen, as shown in figure B. A little consideration will show that the stress or load necessary to break away the specimen is less than the maximum stress. So the stress is therefore reduced until the specimen breaks away at the point F. The stress corresponding to the point F is known as a breaking stress. So we have seen that because of reduction or decrease in cross-sectional area of the specimen, a little consideration or a little load will be necessarily for breaking away of the specimen because there is a decrease in cross-section area. So the stress therefore reduced until the specimen breaks away. The breaking stress appears to be somewhat misleading as the formation of a neck takes place at E, which reduces the cross-section area. It causes the specimen suddenly to fail at F. If for each value of the strain between E and F, the tensile load is divided by the reduced cross-sectional area at the narrowest part of the neck, then the true stress-strain curve will follow the dotted line EG. However, it is established practice to calculate strain on the basis of original cross-section area of the specimen. Let's see this. So I want to see the percentage of reduction in area. Percentage reduction in area. It is the difference between the original cross-section area and the cross-section area at the neck, that is where the fracture takes place. This difference is expressed as a percentage of the original cross-section area. Let A be equal to original cross-section area and capital A, the small a be equal to cross-sectional area at the neck. So then reduction in area will be equal to capital A minus small a. And the percentage reduction in area will be equal to capital A minus small a over capital area A, which means the original area of the specimen. The other item that we would like to focus is about percentage elongation. Percentage elongation. It is the percentage increase in standard gauge. Percentage elongation. It is the percentage increase in the standard gauge length, that is original length. We term it is standard gauge length, original one, obtained by measuring the fractured specimen after bringing the broken parts together. So let's say L, gauge length or original length, small l, and the capital L, length of specimen after fracture or final length. So elongation can be determined by the second length or final length minus the original length. And the percentage elongation can be determined by the final length minus the original length over original length multiplying by 100, you get the percentage elongation. The percentage elongation gives a measure of ductility of a metal under test. That's the essence of finding the percentage of elongation in order to do some comparisons of material properties. The percentage elongation gives a measure of ductility of the metal under test. The amount of local extensions depends upon the material and also on the transverse dimensions of the test piece or specimen. Since the specimens are to be made from bars, strips, sheets, wires, forgings, castings, etc., therefore it is not possible to make all specimens of one standard size. Since the dimensions of the specimen influence the result, therefore some standard means of comparison of results are necessary. In order to have the comparison, we need to focus on some factors to be taken. As a result of the series of experiments, Barber established a law that is in tension similar to test pieces, deforming similarly, and the two test pieces are said to be similar if they have the same value of original L over radical A, where L is the gauge length and A is the cross-section area. So we had regarding the Barber, who established the law that is governing the tension in testing this material. A little consideration will show that the same material will give the same percentage elongation and a percentage of reduction in area because of having the same property of the material. It has been found experimentally by Unwin that the general extension up to the maximum load is proportional to the gauge length, original length, of the test piece, and that the local extension maximum load to the breaking load is proportional to the square root of the cross-section area. Let's see. So according to Unwin's formula, the increase in length can be determined in the formula. That is the change of length. So we have the constant here for where L is the gauge length or original length, A refers to cross-sectional area, and B and C are constants depending upon the quality of the material. The values of B and C are determined by finding the values of change in length for two test pieces of known length L and area capital A. So, stresses and strains in bars of varying sections. In the previous slides, we have discussed the procedures of obtaining stress and strain in bars of uniform cross-section area. But sometimes we come across bars of varying sections in which we require to find the stress and strain as well. So the procedure for finding out the stresses and the strains in the same section is slightly different. So types of bars of varying sections. Though there are many types of bars of varying sections in the field of strength of materials, yet the following are important from the subject point of view. Bars of different sections, bars of uniformly tapering sections, bars of composite sections. Also, all these are employed in our engineering works. So we need to know how we can come up with the stresses and strain respectively. How one can undergo analysis for bar of composite sections. So with the composite sections, a bar made up of 2 or more bars of equal length, but of different materials, rigidly fixed with each other and behaving as one unit. We can have some kind of component that can be made of different materials. So this is an example. A unit, 1 unit for extension or compression, when subjected to an axial tension or compressive load, is called a composite bar. So you can see if this is one type of material and this is second type of material, but they are all fixed, they cannot extend differently. Even both ends they are fixed to both ends, so they are having the same length L, and the same force is applied to both at a go, that is P. You can see that. The bars are joined in such a manner that they extend or contract as one, as a unity, or equally when subjected to tension or compression. For the composite bar, the following 2 points are very important. The extension or compression contraction in each bar is equal. Hence, deformation per unit length, that is strain, in each bar is equal. You have to remember that the strain for both, if at all they are different material, will be equal. So, second point to note, the total external load on the composite bar is equal to sum of the loads carried by each different material. The total external load on the composite bar is equal to the sum of the loads carried by each different material. That means if you have got 3, that you have to add and be equal to the total of external. The resisting force provided by the loads of the object would be summed and equated to the total external force supplied or subjected to. Let's see now for the composite bar. One can come up with that kind of formula. Consider composite bar made up of 2 different materials as shown in the figure below. Let P be the total load on the bar. Our P is here, so this is the total load or total force. And L1, length of the bar 1, L1, and L2 as indicated. So this is load, this is the bar 1 and the bar 2, given our length L. So I've said we term L1 and L2, area 1 is respectively, and area 2 for the bar. Likewise, Young modulus or modulus of elasticity 1 and 2 for the second bar. Also P1 and P2, load shared by bar 1, load shared or load experienced by bar 2. Likewise, stress for the first bar and stress for the second bar. Everything has been shown. So now, on how to determine the total force, The total load on the composite bar is equal to the sum of the load carried by the two bars. The first bar and the second bar, if you sum up, you get the total load, which is equal to the external force. The stress induced in bar 1, you will work out differently. Load carried by bar 1 over area of cross-section of the bar 1. So P1 to area 1. In order now to determine the P1 or load 1, force experienced in the load 1 will be equal to stress on the bar 1 to the cross-section of the bar 1 as indicated here. Likewise, stress induced in the bar 2, the formula is the same or is equal, we can say, up to force or load on bar 2 is equal to stress on bar 2 area or cross-section area of the bar 2. Substituting the values of P1 and P2 in the equation 1, we get, this was for P1 and P2. So, since the ends of the two bars are rigidly connected or clamped, each bar will change in length by the same amount. Also, the length of each bar is the same, and hence the ratio of change in length of the original length, that is strain, mind you, will be the same for each bar. So strain in bar 1, strain in bar 2. Strain in bar 1 is equal to stress induced in bar 1 over Young modulus of bar 1. Likewise, for the second bar, if we want to determine strain, it is stress induced in bar 2 over Young modulus or modulus of rigidity in bar 2. So one can come up with the given formula. Bear in mind that we have said that strain in bar 1 is equal to strain in bar 2 because they are fixed on both ends. So the increase is the same for each bar. However, they differ in material. So strain for bar 1, strain for bar 2. So making this stress for bar 1 subject, or making stress 2 or stress for bar 2 subject in our expression, one can come up with such kind of a formula. From the equation 4 and 5, the stresses can be determined by substituting the values of stress 1 and 2 in equations 2 and 3 in the load carried by different materials may be computed. This makes the end of this part. Thank you. Let's continue with the temperature or thermal stresses. We have got stresses that is a result of temperature change or being subjected to thermal. So here is the source of heat, and the object is subjected to heat, and it causes some deformation of the object due to heat, subjected to it. It has been established since a long time that whenever there is some increase or decrease in the temperature of the body, it causes the body to expand or contract. A little consideration will be shown here. If the body is allowed to expand or contract freely, the rise or fall of the temperature, no stresses are induced in the object. If the object is subjected to heat, of which can cause it to expand, but the body, if it is left freely to expand, no stresses can be induced in it if it is left to contract by itself and no force to restrict it. But if the deformation of the object, the body is prevented, if the deformation of the body is prevented, the body is not allowed to expand or to contract freely, some stresses are induced in the body. Such stresses are called thermal stresses or temperature stresses. The corresponding strain are called the thermal strain or temperature strain. That means thermal stresses are the stresses induced in the body due to the change in temperature. Mind you, if these changes of temperature to the body, if the body is left freely to expand or to contract, one cannot notice the stresses because there will be no deformation of the body. But once it's restricted or controlled, you can now experience some stresses, and finally you can come up to the strain. Thermal stress in simple bars. The thermal stresses or strain in a simple bar may be found out as discussed below. One can calculate the amount of deformation due to the change of temperature with the assumption that the bar is free to expand or contract. Calculate the load required to bring the deformed bar to original length. Calculate the stress and the strain in the bar caused by this load. One can come up with such kind of calculations regarding the thermal stresses in a simple bar. Thermal stresses or strain may also be found first by finding out amount of deformation due to change in temperature, and then finding out the thermal strain to the deformation. The thermal stress may now be found out from the thermal strain as usual. Consider a body which is heated to a certain temperature. Let's say for our case, we have got the object or the load that is initially the AB with the length L, but when it's subjected to some heat, the body tends to increase or to extend, change in L. So there is a change in what? In length. But for B, you can see the force P that is pushing inside or opposite to the force that is being applied due to the change of temperature, which is thermal stress. We will see on how one can come up with that given formula. So L, small l, original length of the body, and capital T, that's the rise or increase in temperature. So we have seen that E, capital E, is for Young modulus or modulus of rigidity. Alpha, coefficient of linear expansion. And change in L, extension of rod due to rise in temperature. If the rod is free to expand, then the extension of the rod, increase in length due to increase in temperature, is given by, as you can see here. So the change, the increase in length can be determined by the alpha, coefficient of linear expansion, change in temperature, and the original length. For case 1, the end of the bar is, for the ends of the bar are fixed. Let's see for case 1, if the bar is fixed to rigid support so that its expansion is prevented. It means it's not free, it's not expanding freely. The compressive strain is induced in the bar. So one can come up with such kind of a formula. Strain, that means the change of length of original length is equal to strain. You remember here is the formula for extension or change in length of original length is equal to strain alpha, coefficient over original length. Mind you, it was the original length here over original length. So they have reduced the original length to original length, and the remaining alpha to change in temperature, you come up to strain. So stress over strain is equal to Young modulus. Stress sigma, strain times Young modulus is equal to strain Young modulus to alpha, change in temperature, Young modulus. Likewise, for stress and strain, when the support yields, if the support yield by the amount equal to delta, the actual expansion that has taken place can be indicated in that expression. Expansion is due to rise in temperature, alpha. So strain, one can determine such kind of expression. The value of alpha, that's coefficient of linear expansion of material in everyday use, are given below, or some few are provided for application or comparison. Material, for example, material steel, coefficient of linear expansion. It's indicated here. Just a few to show you. Wrought iron or cast iron, aluminum, copper, brass, and bronze, they are grouped for 17 times 10 power negative 6 up to 18 times 10 power negative 6. So thermal stresses in compost bars. Let's see for compost bars. Whenever there is some increase or decrease in the temperature of a bar consisting of 2 or more different materials, it causes the bar to expand or contract. On account of a different coefficient of linear expansion of the two materials do not expand or contract by the same amount, but expand or contract by different amounts. You can see that they are of different, this is steel and the other one is brass, but they can expand differently regarding their coefficient of expansion or their structure of atoms within each element. Now consider the composite bar consisting of two members, a bar of steel and another of brass is shown. If the component members of the bar, that is steel and brass, could have been free to expand when subjected to heat, then no internal stresses would have been induced. That means no stress if there is no what? Deformation. But since the two members are rigidly fixed, they are clamped. Therefore, the composite bar as a whole would expand by the same amount. Brass expands more than steel according to its structure, atomic structure. Because of the coefficient of linear expansion of the brass is greater than that of steel. However, both members are not free to expand. Therefore, the expansion of the composite bar as a whole will be less than that of brass, but more than that of steel, as shown in figure B, we will see. One expands more than the other, but they will meet in between because one will have to pull the other one, which is expanding slowly. Therefore, brass will be subjected to compressive force, the one that expands more, because there is one who is delaying to expand, whereas the steel will be subjected to tensile force. The stress induced in the brass will be compressive, whereas the stress in the steel will be tensile. So the abbreviation, now let that is stress for brass, strain for brass, and the coefficient of expansion for brass, area, cross-sectional area for brass. They are here, corresponding values for steel, and the actual expansion of the composite bar. As the compressive load on the brass is equal to the tensile load on the steel, therefore you can equate in that manner, in that way. As the compressive load on the brass is equal to the tensile load on the steel, therefore one can come up with such kind of expression for the brass and the steel. Also, we know that actual expansion of steel is equal to actual expansion of brass. But the actual expansion of steel, the expansion of steel plus expansion due to tensile stress in steel. There is free expansion, the initial expansion, but plus the expansion that is caused by the brass. Remember that the brass has more expansion rate compared to the steel. So it happens that it supports the steel to expand because it has already expanded to some distance. So it forces this one to go together with the steel. So this is the expansion due to steel stress, tensile stress in steel. And the actual expansion of brass. Remember, initially there is expansion of brass by itself, and there is a contraction due to compressive stress induced in the brass due to resistance of going together with the steel, which is going very slowly. So there is a pulling back because this one is in a higher rate of expanding, but this one, because they are bonded together, is restricting this one to continue with its path. is termed as minus contraction due to compressive stress induced in the brass. This is the formula one can come up with. Since the actual expansion of steel is equal to actual expansion of brass, so expression for the two bars, that is brass and steel, can be indicated in that manner. Brass and steel, where T rise of temperature. Strain energy and impact loading. So let's have an introduction to this part. Whenever some load is attached to a hanging wire, it extends, or the wire tends to extend because of the load that is hanging on that wire downwards. A little consideration would be shown that when the load moves downwards, it loses its potential energy. That is energy possessed by the body by virtue of its position. This energy is absorbed or stored in the stretched wire, which may be released by removing the load. If you have got a spring, this can be well elaborated. On removing the load, the wire will spring back to its original position because the load is no longer there. So the spring will tend to go back to its original position. This energy, which is absorbed in a bar, when strained within its elastic limit, it is known as strain energy. In other words, the energy which is absorbed in the body due to the strain effect is known as strain energy. The straining effect may be due to gradual applied load, or suddenly applied load, or load within impact. It has been experimentally found that this strain energy is always capable of doing some work. The amount of strain energy in your body is found out by principle of work. That is, the strain energy stored in the body is equal to the work done by the applied load in stretching the body. So mathematically, one can say strain energy is equal to work done. Before deriving the expressions for strain energy stored in a body due to gradually applied load, or suddenly applied load, or loaded with an impact, the following terms will be defined: resilience, proof of resilience, modulus of resilience. Let's see resilience. The total strain energy stored in a body is commonly, this one is what we refer to resilience. Whenever the straining force is removed from the strained body, the body is capable of doing work. Whenever the straining force is removed from the strained body, the body is capable of doing work. Hence, the resilience is also defined as the capacity of a strained body for doing work on the removal of stretching body. Second part, for the proof of resilience, the maximum strain energy which can be stored in a body is known as proof resilience. The strain energy stored in a body will be maximum when the body is stressed up to the elastic limit. Hence, the proof resistance is the quantity of strain energy stored in the body when strained up to the elastic limit. So the corresponding stress is also known as proof stress. Modulus of resilience, it is defined as the proof resistance of a material per unit volume. It is an important property of a material which mathematically can be expressed as proof of resilience over volume of the body will be equated to modulus of resilience. So let's see the types of loading. A load may act in either of the following three ways. Can gradually applied load or suddenly applied load. The other way, a load applied with impact or impact load. So these are the types of loading, one after the other. So strain energy stored in a body when the load is gradually applied. It is the most common and a practical way of loading a body, in which the loading starts from zero and increases gradually till the body is fully loaded. For example, when we lower a body with the help of a crane, the body first touches the platform on which it is to be placed. On further releasing the chain, the platform goes on loading till it is fully loaded by the body. This is the case of gradually applied load. So you can see a sketch here, how it changes from 0 up to K. Below shows load extension diagram of a body under tensile test up to elastic limit. The tensile load is increased gradually from 0 to the value P, and extension of the body increases from 0 to the value of X or K. The load P performs work in stretching the body. This work will be stored in a body as a strain energy which is recoverable after the load P is removed. Now, consider a metallic bar subjected to a gradual load. Let's say P, B, load gradual applied, and A, cross-section area of the bar, L, length of the bar, modulus elasticity of the bar material. This is already covered. Okay, deformation of the bar due to the load, strain energy stored in the body, volume of the body. Since the load applied is gradual and varies from 0 to P, therefore the average load is equal to P over 2. So work done is equal to, as we know, work done is equal to force times distance, average load times deformation. So, but P is equal to stress times area. So our P here, divided by 2, the average load times change in length will be equal to P, that's our load, average load, over, the P, which is over 2, the average load, times strain times original length. So one can come up with the formula that I have times stress times strain times volume, you get the work done. Since the strain energy stored is also equal to the work done, therefore strain energy stored can be given such kind of a formula. We also know that the modulus of resilience is equal to strain energy per unit volume. One also can come up with such kind of a formula, modulus of resilience, being derived from the above stress squared over 2 young modulus, you get to modulus of resilience. Strain energy stored in a body when the load is suddenly applied. Sometimes in factories and the workshops, the load is suddenly applied on a body. For example, when we lower a body with the help of a crane, the body is first of all just above the platform on which it is to be placed. If the chain breaks at once, at this moment, the whole load of the body begins to act on the platform. This is the case of a suddenly applied load. Now, consider a bar subjected to a sudden load. So let P be load applied suddenly. A, cross-sectional area of the bar, L, length of the bar, where E, capital E, is the modulus of elasticity of the material, and the deformation of the bar, that is, this will indicate the strain, stress induced by the application of the sudden load. Since the load is applied suddenly, therefore the load P is constant throughout the process of deformation of the bar. So work done, as usual, is equal to force times distance, load times deformation. So our formula is equal to work done is equal to the applied force times change in length. But we know that strain energy is stored. So work done is equal to stress squared over twice Young modulus times cross-section area times original length. Since the strain energy stored is equal to the work done, therefore, one can come up with such kind of expression, but the change in length is equal to stress times original length over Young modulus. Therefore, the stress squared over twice Young modulus times cross-section area times L, which is original length, is equal to the load applied times cross-section, times stress times original length to Young modulus. This will be our formula for the load applied suddenly. It means that the stress induced in this case is twice the stress induced when the same load is applied gradually. If you compare to the load that has been applied gradually, will be doubled. And once the stress is obtained, the corresponding instantaneous deformation and the strain energy may be found as usual. Strain load. Let's see now when load is applied with impact. Sometimes in factories or workshop, as we have seen, the impact load is applied on a body. For example, when we lower a body with the help of a crane and the chain breaks, while the load is being lowered and the load falls through a distance before it touches the platform. This is the case of a load applied with impact. Mind you, before it touches the platform, this is, there is a considerable distance. This makes the difference with the suddenly applied load. Now consider a bar subject to a load applied with impact as shown. P, load applied with impact, cross-sectional area of the bar. E, modulus of elasticity of the bar material. L, length of the bar, change in length, deformation of the bar as a result of this load. It's a deformation of the bar as a result of the load. So you can see a vertical rod and the distance h where the load can move, or when it's dropped to and the final, you can see here the difference. There is a change here, the increase, the deformation of the bar as a result of this load. So there is increase of load, change. It was supposed to be here, collar, but it has moved due to the impact. So stress induced by the application of this load with impact, h being the height through which the load will fall before impacting the collar of the bar. So work done is equal to load times distance moved, as expressed here. The diagram can clearly express, and the energy stored, labeled U. This is our formula for the energy stored when there is impact load. Yeah, it was the same. There is increase of. So here, L, mind you, is for H plus change in length. So the total H now becomes H plus change in length. So it's equal to the stored energy. So if in substitution, one can come up with a quadratic equation. Once the stress is obtained, the corresponding instantaneous deformation, change in length, or the strain, energy stored may be found as usual. So this is the formula one can come up with. When the change in length is very, very small as compared to H, then assumption can be taken as work done is equal to PH, and the formula becomes stress is equal to radical sine twice Young modulus, load times the load applied times the height over cross-section area over times the original length. That's the formula. Now can change once the change in length becomes very, very small. So can be assumed to be work done is equal to P times H, where H can be derived from this expression, and one can come up with such kind of a formula. When a force is applied tangentially on the first CD, as we saw for the shear force, shear stress, and the shear strain, modulus of rigidity or shear modulus can be determined for such kind of force. So as well, work done is equal to the average force, that is P over 2, times the change distance, that's D to D1. But mind you, D to D1 is equal to AD times the angle thou, area of the top face, which is A, is equal to CD times length L, hence P is equal to tau. Mind you, remember this tau, times DC times L. This is regarding our sketch here. See the angle we are referring to, that's D to D1. There is a change here in length. So work done can be calculated by a half shear stress times volume times shear strain, which mathematically can be work done is equal to a half tau times volume times tau, which is over n, which now can be tau squared times volume times twice n, since the energy stored is also equal to the work done. Therefore, energy stored can be provided in such kind of a expression. We also know that modulus of resilience is equal to strain energy per unit volume. So one also can have kind of work done or stored energy. This makes the end of this part.